There are two use cases of ASNI Read Reorder Buffer. It allows same ID reads to be outstanding to different destinations. If same ID reads are outstanding to different destinations, the responses can arrive in any order. However, the manager is expecting the responses in the order of issuance. So, Read Reorder Buffer is used to ensure correct ordering. When the ASNI encounters a read transaction with the same AR ID as an outstanding transaction to a different destination, it reserves read reorder buffer entries equal to AR length plus 1. This is the burst length. When the read reorder buffer is full, it goes back to single slave per ID. The second use is for merging return read data. It is possible that the ASNI has a larger data width than the downstream AMNI. When sending read requests to an AMNI with lower data width, the ASNI allocates one single entry in the read reorder buffer per transaction, regardless of the length of the burst. The read reorder buffer collects the returning partial read data and merges it according to the data width of the ASNI. If there is no read reorder buffer space, then the transaction is stalled. The read reorder buffer can be sized 1 to 512 entries, and the tooling defaults it to 32. By default, ASNI Tower implements the read reorder buffer as a series of flops. For flop-based ROBs, large ROB depths can have a significant impact on the area. ASNI Tower also supports RAM-based read reorder buffer implementation. Using a RAM-based implementation for large read reorder buffers significantly reduces the area as compared to a flop-based implementation. We recommend RAM-based implementation when the number of entries is greater than 64. Now, using this knowledge, let's try to optimize the read reorder buffer depth in tooling. Since the tooling defaults the read reorder buffer depth to 32, there's often scope for optimization based on the traffic requirements. The average read reorder buffer occupancy can be found in the result statistics of the performance test case under the occupancy category. The average read reorder buffer occupancy for each of the ASNIs turns out to be 0. The performance tool also allows you to check if there were any read request stalls due to the read reorder buffer being full. This can be found under the PMU category. We expect this to be 0 since the average read reorder buffer occupancy was 0. For some other traffic case, if this was non-zero, then that suggests that increasing the read reorder buffer depth may potentially avoid the stalls and improve the bandwidth. The nature of our traffic is such that it does not fall into the two cases of read reorder buffer mentioned earlier. Looking at the traffic profile, we see that 20% of the AXI and ASIT reads use the same ID. But since the accesses are to the same destination, it does not need any allocation in the read reorder buffer. So, we can safely set the read reorder buffer depths to 1 for all the ASNIs, and that will save us area. We can modify the read reorder buffer depth from the canvas by selecting the complete interface and clicking on the parameters under the property editor. The read reorder configuration parameter can be found under tracker sizes. Based on our traffic, we will set this to 1 for this demonstration. The read reorder buffer depth can be modified on all the other ASNIs in a similar fashion. Let's take a look at the area report. The total area for this configuration has reduced to 36,073 or 36073. Deeper read reorder buffers increase the area footprint of the ASNI. We recommend sizing them carefully based on your network's traffic requirements. If you're not sure about the read reorder buffer requirements, you may start with a deeper read reorder buffer, run a performance test case, and use the read reorder buffer occupancy reported by the performance tool to refine its depth.